Imagine for a second that you are just standing in the middle of a typical older wooden house in the suburbs. Just a standard timber frame living room.
Right, very standard.
Now, teleport yourself from there and imagine you are standing right in the center of the rotunda of the United States Capitol building in Washington, D.C.
Surrounded by all that massive, sweeping architecture.
Exactly. Now, if you had to guess which of those two environments is exposing you to more radiation at this exact second, what would you say?
I mean, most people would assume it's a trick question.
Right. Or maybe they'd think there's some secret government antenna hidden in the Capitol or something. But it's actually the Capitol building. And the reason has literally nothing to do with technology.
It's the stone.
Yes, the stone. The Capitol is built with these massive amounts of granite. And granite naturally contains trace amounts of uranium. So you are absorbing more radiation taking a tour of the nation's capital than you are just sitting on your own wooden porch.
Which is just one of those facts that completely shatters the pop culture image we have of radiation. I mean, we are so conditioned by comic books and movies to think of radiation as this, glowing green ooze.
Yeah, or some unnatural man-made poison that only exists inside concrete bunkers.
Or at the center of a nuclear reactor. But the reality is that the universe is just humming with it. It is baked into the earth, it is raining down from the sky, and it is built into the very cells of our bodies.
And that is the exact mission we have for this deep dive today. We want to completely demystify radiation for you.
Strip away that sci-fi fear factor.
Exactly. We want to help you, listening right now, understand the invisible forces that are passing through your body at this very moment. And to do that, we've brought together a really incredible stack of sources.
We are pulling data from official reports by the U.S. Nuclear Regulatory Commission, or the NRC.
Plus, we have these incredibly dense, fascinating physics handbooks from the International Atomic Energy Agency, the IAEA.
And we're also looking at industry standard safety and biological protocols from the protection experts at Barrier Technologies.
So a lot of heavy material to go through. But the overarching theme across all those sources is that radiation is, at its core, the communication method of the universe.
It really is. It is simply how energy moves from one place to another.
Right. And to truly understand why some of it is completely harmless, like the radio waves bringing this audio to your device right now, and why some of it can literally break human DNA, we have to take a journey.
A journey that spans the absolute extremes of scale. We need to start by zooming all the way into the subatomic scale, looking at the very building blocks of reality.
And then eventually we'll zoom all the way out to the cosmos. So let's start zooming in then.
Sounds good.
Before we can even talk about lead aprons or nuclear reactors or X-rays at the dentist, we have to look at the fundamental forces that dictate how matter actually holds together.
Right, because the IAEA handbook spends a lot of time establishing this. If you don't understand the glue of the universe, you really can't understand what happens when that glue comes apart.
Exactly. So the framework they lay out is based on the 4 fundamental forces of nature.
Every single interaction in the universe, from a star going supernova all the way down to a magnet sticking to your refrigerator, is governed by one of these 4.
And those are the strong force, the electromagnetic force, the weak force, and the gravitational force.
Yes. And the disparity in how powerful these forces are is just staggering. It is almost impossible to visualize, but we can use a relative scale to help.
Let's do that. So let's assign the strong nuclear force a strength level of 1.
Right. Oh, 1. It is the reigning champion of the universe. Its entire job is to hold the nucleus of an atom together.
Which is actually a really tough job, right?
Well,
because protons have a positive charge.
Exactly. And as we know from playing with magnets as kids, charges repel each other violently.
So the strong force acts like an incredibly powerful bungee cord,
binding those positively charged protons together in the nucleus, completely ignoring their intense desire to just fly apart.
So if the strong force is our baseline of 1, where does the electromagnetic force sit?
Electromagnetism is roughly 1/137.
Oh, wow. Okay.
Yeah, so it's vastly weaker than the strong force, but still incredibly powerful. This is the force that governs light, electricity, magnets, and the chemical bonds between atoms.
Okay, then you drop down to the weak force, which governs radioactive decay and the fusion happening inside the sun. Where is that on the scale?
That force sits at an unimaginably faint 10 to the power of -6.
That is quite the drop. which leaves gravity. And I gotta say, this is the one that always throws my brain for a loop
Gravity's tricky.
because it holds us to the Earth, keeps the Earth orbiting the sun. It feels like the absolute most dominant force in our everyday lives.
But on a quantum level, it is the weakest by a comical margin. On our scale, gravity has a relative strength of 10 to the power of -39.
That is just, I can't even picture a number that small.
To put that into perspective, think about picking up a paperclip with a tiny fridge magnet.
Okay.
That tiny magnet is using the electromagnetic force to completely overpower the gravitational pull of the entire planet Earth, trying to hold that paperclip down.
That is a brilliant way to picture it. The entire mass of the Earth is literally losing a tug of war to a cheap piece of plastic on my fridge.
Exactly. So those forces are the rules of the game. But what are the pieces on the board?
Right. The IAEA source breaks down the particles that actually make up matter into two main families. Let's talk about the first one.
The first family is the quarks. Quarks are the particles that actually feel that strong force we just talked about.
They clump together to form protons and neutrons, right?
Yes, which make up the heavy center of every atom. And physicists use a really whimsical naming convention for them. Quarks have fractional electric charges, but they also have a different kind of charge related to the strong force, which physicists decided to call color.
But they don't actually have a visual color. Right. Like if I could shrink down and look at a quark, it wouldn't look like a tiny red marble.
No, not at all. Color is just a mathematical placeholder. Because there are 3 types of the strong charge, they name them red, blue, and green.
Because those 3 colors of light combine to make white.
Exactly, a neutral state. It's just an elegant, sort of quirky way to keep track of the math.
I just love how physicists hit a wall of incomprehensible quantum mechanics and just start naming things like they're decorating a nursery.
It keeps things interesting.
So that's the quarks. What's the second family?
The leptons. These are the particles that do not interact with the strong force at all. They are entirely immune to it.
And the most famous lepton, the one that essentially dictates all of chemistry and electronics, is the electron.
That's right. The lepton family also includes heavier cousins like the muon and the tau, as well as their associated neutrinos.
Neutrinos are wild. They're these ghostly, nearly massless particles that just zip through the universe, barely interacting with anything.
Right. So we have our forces and we have our particles, quarks locking together to form the heavy nucleus, and leptons, specifically electrons, buzzing around the outside.
But to tie this all to radiation, we have to introduce a few of the fundamental constants that govern how this entire system operates.
Yes, the math that makes it all work.
The IAEA handbook lists the speed of light in a vacuum, which we represent with the letter C. That speed is roughly 300 million meters every single second.
It is the ultimate speed limit of the universe. Nothing goes faster.
Right. Then, to bridge the gap between the unimaginably small quantum world and the macroscopic world of chemicals and materials that we can actually weigh in a lab, we have Avogadro's number.
Ah, yes. 6.022 times 10 to the 23rd.
Which tells us how many atoms or molecules are in a specific volume of a substance, so we can calculate mass and density.
But the piece of the puzzle that truly explains radiation is Albert Einstein's mass-energy equivalence, the most famous equation in human history.
E equals mc squared.
Energy equals mass times the speed of light squared. That equation fundamentally altered our understanding of reality.
How so? Like, before Einstein, what did people think?
Well, before Einstein, humanity thought that a physical object mass was one thing, and the energy it possessed, like heat or momentum, was a completely separate property.
But E equals mc squared proved that mass and energy are actually the exact same underlying currency.
Exactly. Mass is simply energy that has been highly condensed and frozen into a physical form, and energy is just mass that has been liberated.
And when that energy is liberated, when it is unspooled from a physical object and goes traveling freely through space, that is what we call radiation.
Yes. It's energy on the move, and the way we categorize that moving energy is through the electromagnetic spectrum.
The EM spectrum. This is a classification system based entirely on the wave-like properties of this traveling energy.
Right. All electromagnetic radiation travels at the speed of light, but it oscillates, it vibrates.
And we categorize it based on its frequency, like how many times it vibrates per second, or its wavelength, which is the physical distance between the peaks of those waves.
Looking at the history of how humans discovered the EM spectrum is just fascinating because for 99% of human history, we were only aware of one tiny microscopic sliver of it.
Visible light.
Right. The light our eyes evolved to detect has a wavelength between roughly 380 and 750 nanometers, but the full spectrum is unimaginably wider than that.
Let's walk through it, starting from the absolute lowest energy with the longest, laziest waves.
Down at the very bottom of the energy scale, we have radio waves. The wavelength of a single radio wave can be indefinitely long. We're talking about the distance between peaks being hundreds or even thousands of kilometers.
Because they are so long and low energy, they were purely theoretical for a long time, weren't they?
They were. It wasn't until 1887 that a German physicist named Heinrich Hertz actually built an apparatus to prove they existed.
The way he did it is such a classic piece of 19th century garage science.
Oh, totally.
He built a circuit with a gap in it and applied a high voltage until a spark jumped across the gap. He theorized that the spark would send invisible waves rippling through the air.
So across the room, he set up a simple loop of wire with its own tiny gap.
And when the spark fired on the main transmitter, a tiny sympathetic spark jumped across the receiver loop across the room, with literally no wires connecting them.
Hertz had generated and detected invisible electromagnetic waves. He proved that they traveled at the speed of light and that they could be reflected by metal just like visible light is reflected by a mirror.
Amazing. So moving up the spectrum, as the waves get shorter and the frequency gets higher, we reach microwaves.
These range from about 10 centimeters down to 1 millimeter. We use them for radar, satellite communications, and obviously heating up leftovers.
The mechanism of how a microwave oven works is a great example of physics in action.
It really is. Microwaves are tuned to a frequency that perfectly resonates with polar molecules like water.
So when the microwave energy hits the water molecules in your food, it causes them to physically flip and rotate back and forth incredibly fast.
And all that microscopic friction and rotation generates bulk heat. That's how your soup gets hot.
Keep moving up the dial, shrinking the wavelength further, and we hit infrared. And the discovery of infrared is one of my favorite stories in the history of science.
It's a great one. It happened in the year 1800.
Right. The astronomer William Herschel was using a glass prism to split sunlight into a rainbow on a table, exactly like Isaac Newton did. Herschel wanted to know if different colors of light contained different amounts of heat.
So he takes a thermometer and places it in the blue light, then the yellow light, then the red light. And as he moves toward the red end of the spectrum, the temperature reading goes up.
But then he sets up a control. He places the thermometer just past the red light in the dark shadow where there is absolutely no visible light falling on the table.
He fully expects it to read room temperature.
Instead, the thermometer in the dark spikes higher than any of the visible colors.
Herschel realized there had to be an invisible form of light shining on that exact spot, carrying immense amounts of heat. He termed them calorific rays.
Calorific rays, which today we know as infrared radiation.
Yes, which is the heat signature emitted by everything from warm human bodies to distant galaxies.
That discovery essentially broke the dam. Scientists suddenly realized there was invisible light hiding everywhere.
Right. The very next year, in 1801, Johann Wilhelm Ritter heard about Herschel's experiment and thought, well, if there is invisible light below the red end of the rainbow, there has to be invisible light above the violet end.
So Ritter used silver chloride, a chemical that visibly darkens when exposed to sunlight. He painted it on strips of paper and placed them across the visible spectrum.
The paper darkens slowly in the red light and faster in the violet light.
But when he placed a strip in the dark area just beyond the violet light, it turned pitch black almost instantly.
He called them chemical rays because of their ability to trigger chemical reactions. We now call this ultraviolet or UV radiation.
And if we keep going up the scale, past UV, into wavelengths that are smaller than atoms, we hit X-rays.
Wilhelm Röntgen stumbled onto these in 1895 while experimenting with electrical discharges in vacuum tubes.
He noticed that a fluorescent screen across his lab started glowing whenever he turned his machine on, even if he covered the tube with heavy black cardboard.
He didn't know what kind of rays they were, so he used the mathematical symbol for the unknown, X, and the name X-rays just stuck permanently.
It's kind of funny how literal scientists are with naming things. And finally, at the absolute top of the EM spectrum, with the shortest possible wavelengths and the highest, most terrifying frequencies, we have gamma rays.
Yes, these were identified by Paul Villard in 1900 while he was studying the radiation emitted by the element radium.
So we have this massive continuous spectrum stretching from miles-long radio waves down to microscopic gamma rays. But to really grasp how they interact with human biology, we have to introduce a concept that kind of breaks human intuition.
Wave-particle duality.
Exactly. Up until this point, we've been describing radiation as a wave rippling through a pond. But that is only half the truth.
Right. Electromagnetic radiation travels through the vacuum of space as a continuous waves, but the moment it interacts with physical matter, the moment it hits an atom, it behaves like a discrete, indivisible bullet of energy.
And we call these bullets photons.
Yes. And there is a strict mathematical relationship between the wave and the bullet, dictated by the equation E equals hc over lambda.
Energy equals Planck's constant times the speed of light, all divided by the wavelength.
What this equation tells us is that the energy of the individual photon is inversely proportional to its wavelength.
Meaning the longer the wave, the weaker the bullet. A massive radio wave stretching for a mile delivers photons that possess almost zero energy.
But a tiny, highly compressed gamma ray delivers a photon that hits with the force of a subatomic sledgehammer.
A great way to visualize the entire spectrum is to think of it like a giant cosmic piano.
Oh, I like that analogy.
You have these deep, rumbling, incredibly long wavelengths at the low end of the keyboard, the radio waves and microwaves. Up at the top right of the keyboard, you have the frantic, tight, incredibly high-energy gamma rays and X-rays.
And human biology. Our eyes evolved to detect exactly one single octave right in the middle of that keyboard. We are entirely blind and deaf to the rest of the instrument.
I just love that visual. But it raises what is arguably the most important question of this entire deep dive.
Let's hear it.
If visible light, the Wi-Fi signal routing this audio, and the X-ray machine at the hospital are all fundamentally the exact same physical phenomena, just playing different notes on that piano, why do they have such wildly different effects on our bodies?
That's the big question.
Why does visible light safely bounce off an apple so I can see it, while an X-ray can mutate my cellular DNA?
That question brings us to a physical threshold that dictates all radiation safety. We can call it the Great Divide.
The Great Divide.
Yes. This is the exact point on the cosmic piano where the notes get so high-pitched and the photons pack so much raw kinetic energy that they stop just vibrating the matter they hit and they start physically tearing it apart.
This is the dividing line between non-ionizing radiation and ionizing radiation.
Exactly. And we need to define ionizing very carefully because it is the entire ballgame when it comes to understanding health risks.
Right. So what does it actually mean to ionize matter on a quantum level?
Think of an atom as a miniature solar system. You have the heavy nucleus in the center acting like the sun, and the electrons are the planets orbiting around it.
Under normal circumstances, an atom is electrically neutral.
Right. It has the same number of positive protons in the center as it has negative electrons in orbit. They perfectly balance each other out.
It's a stable system.
Yes. To ionize that atom means a photon of radiation comes crashing into that solar system with such immense concentrated energy that it strikes an orbiting electron and ejects it entirely out of the atom.
It knocks the planet out of orbit and sends it flying into deep space.
Precisely. And when the atom loses that negative electron, the balance is broken. The atom is left with a net positive charge. It becomes an ion.
And ejecting that electron requires a very specific minimum amount of energy.
It does. The binding energy holding the outermost electrons to a typical biological molecule, like the carbon and oxygen in your DNA, is roughly 10 electron volts, or 10 eV.
10 eV. That is the magic number. That is the toll you have to pay to break a chemical bond.
So what happens if a photon hits an atom, but it carries less than 10 eV of energy?
If it carries less than 10 eV, it simply bounces off, or it gets absorbed and causes the electron to vibrate and wobble. It might jump to a slightly higher orbit for a fraction of a millisecond, but the gravitational pull of the nucleus holds on.
The chemical bond remains intact. The solar system wobbles, but the planets stay in orbit.
And this describes all non-ionizing radiation. Radio waves, microwaves, infrared, visible light, and the lowest frequencies of ultraviolet.
Correct. All of these notes on the piano are below the 10 eV threshold. The photons in a Wi-Fi signal carry fractions of a single electron volt. They are mathematically, physically incapable of breaking a chemical bond.
So when they hit your body, their low energy impact is just absorbed as physical movement. They cause your molecules to vibrate, rotate, or experience slight electronic excitation,
which our nervous system perceives as heat. When you stand outside on a sunny day, the infrared and visible light photons are physically vibrating your skin molecules and you feel warmth. But your atoms are not being ripped apart.
No, once you cross that 10 eV threshold, you enter the realm of ionizing radiation.
This covers upper ultraviolet, X-rays, and gamma rays. These photons carry hundreds, thousands, or even millions of electron volts.
So when one of these high-energy photons hits an atom in your body, it acts like a rogue comet smashing into a planet.
Exactly. It instantly violently strips the electron away. This forced removal of an electron causes immediate unnatural chemical reactions.
Because that positively charged ion is now highly unstable and will violently seek out a new electron to steal from a neighboring molecule.
And if that cascade of chemical theft happens inside the nucleus of a human cell, it can directly damage the DNA strands.
Which is why the nuance of ultraviolet light is so incredibly important, because the UV band literally straddles this 10 eV Great Divide.
It is the bridge between the safe warmth of the sun and a severe medical hazard. Let's break down UV light, because dermatologists are always talking about UVA, UVB, and UVC, but they rarely explain the physics behind the acronyms.
Yeah, let's get into that. So what's the deal with UVA?
UVA has the longest wavelength and the lowest energy of the three. It is generally below the ionizing threshold. However, it can still transfer enough energy to certain molecules in your skin to create reactive oxygen species-free radicals.
Ah, free radicals.
Right. These radicals bounce around and damage collagen, which is why UVA exposure is the primary driver of premature aging, wrinkles, and sunspots. It's a slow degradation.
Then you move up in frequency to UVB. This is the middle range,
Mm-hmm.
and this is the light that causes a physical sunburn.
Now, UVB is fascinating because it sits right on the edge of the divide. The IAEA source notes that UVB is energetic enough to cause a very specific type of damage to DNA called a thymine dimer.
Okay, a thymine dimer, what is that exactly?
This is a perfect example of a mechanism. Picture a strand of DNA like a twisted ladder. The rungs of the ladder are made of chemical letters pairing up. A always pairs with T and C always pairs with G.
Right.
When a high-energy UVB photon strikes the DNA, if it hits a spot where two thymine molecules are sitting right next to each other on the same side of the ladder, the photon's energy breaks their bonds to the other side.
And causes the two T's to fuse directly to each other.
Exactly. It creates a physical kink or a knot in the DNA ladder. That is a thymine dimer.
Wow. And then what happens when the cell tries to divide?
Well, when your cell naturally tries to divide and replicate, the chemical machinery reading the DNA hits that knot and essentially derails. It copies the genetic code incorrectly.
And that error is a mutation.
Yes. And if that mutation happens in the wrong sequence of genes, it can lead directly to skin cancer.
That is such a clear visualization of how a physics event, like a photon hitting a molecule, translates directly into a biological disease.
Mm-hmm.
And then you have the highest tier, UVC.
UVC is often called vacuum UV. It is fully ionizing, packing well over the 10 eV threshold. It is incredibly dangerous to all biological life. You would shred DNA upon contact.
But the Earth has a built-in defense mechanism against it, right?
We do. UVC is completely absorbed by the Earth's ozone layer and by the diatomic oxygen and nitrogen molecules high up in the atmosphere.
So the UVC photons basically spend all their energy ionizing those atmospheric gases miles above our heads.
Which means essentially zero UVC radiation from the sun ever reaches the surface of the Earth. The atmosphere is literally taking the bullet for us.
Thank goodness for that. Now, understanding this strict mathematical divide of 10 eV brings up a massive cultural debate.
Oh, absolutely.
We constantly hear fear-mongering about living near high-voltage power lines, or the 5G router mutating our cells, or keeping a cell phone in your pocket.
Right, the classic concerns.
If non-ionizing radiation mathematically fundamentally lacks the energy to break a bond and cause a mutation, is this entire debate just a massive public misunderstanding of basic physics?
By and large, yes, it is a misunderstanding. The physics community is unequivocal on this. A photon from a 5G cell tower carries roughly 1 million times less energy than is required to break a DNA bond.
So it is physically impossible for it to cause ionization.
Completely impossible.
But I've read reports that the World Health Organization classifies radio frequency fields as possibly carcinogenic. That phrasing sounds incredibly alarming to the average person.
I understand why it does, but the confusion stems from how scientific classification works versus how the public interprets risk.
Okay, unpack that for me.
The possibly carcinogenic classification simply means that in massive, sprawling population studies, a microscopic statistical link couldn't be definitively 100% ruled out to the absolute satisfaction of every single scientist.
It does not mean a mechanism of harm has actually been found.
Exactly. The only proven, repeatable biological effect of radiofrequency radiation is tissue heating.
Which goes back to the microwave oven analogy.
Right. If you tape a high-powered radio transmitter to your head, you might slightly elevate the temperature of your skin, just like standing near a warm radiator.
And power outputs on consumer devices are heavily regulated to ensure that thermal heating is practically zero anyway.
Exactly. If you are genuinely worried about DNA damage, putting on sunscreen before you check your mail is infinitely more protective than throwing away your Wi-Fi router.
That clears up so much of the noise. Okay, so we've firmly established how electromagnetic waves of light interact with matter. But that is only half the story of radiation.
It is. Because ionization isn't just caused by weightless photons of light, it is also caused by literal, physical pieces of atoms flying through the air at terrifying speeds.
This is where we leave the realm of the electromagnetic spectrum and enter the world of radioactive decay. Welcome to the particle zoo.
The particle zoo. To understand the animals in the zoo, we have to go back to that heavy nucleus at the center of the atom, where the strong force is holding the protons and neutrons together.
Right. Every atom has an atomic number, which is just the count of its protons, and a mass number, which is protons plus neutrons.
For most of the atoms forming your body and the chair you're sitting in, that nucleus is stable. The strong force is perfectly balanced.
But in some elements, especially the incredibly heavy ones near the bottom of the periodic table like uranium or plutonium, the nucleus is too large.
The ratio of protons to neutrons is off, and the nucleus possesses too much internal energy. It is unstable.
It's like a vibrating overpacked suitcase where the latch is just about to fail.
That's a good way to picture it. To reach a stable, lower energy state, that unstable nucleus will spontaneously undergo radioactive decay.
The latch breaks, and the nucleus violently ejects a piece of itself to relieve the pressure.
And the fragments that come shooting out are the particles in our zoo. Alpha particles, beta particles, gamma rays, and neutrons.
Let's meet the first animal, the alpha particle.
An alpha particle is an absolute brute. It is a massive chunk of nuclear material, specifically, a cluster of 2 protons and 2 neutrons bound tightly together.
It is essentially the nucleus of a helium atom.
Yes. Because it contains 2 protons and 0 electrons, it carries a heavy positive charge of +2.
If we think about the danger profile of this particle, that massive size and double charge make it behave like a bulldozer plowing through a china shop.
That is the perfect analogy. Because the alpha particle is so heavy and so highly charged, the moment it gets ejected from a decaying nucleus, it begins interacting violently with everything around it.
It bulldozes through the electron clouds of neighboring atoms, using its +2 charge to rip electrons away with incredible force.
It has the absolute highest ionization power of any common radiation. It is roughly 20 times more effective at destroying cellular tissue than a gamma ray.
Which sounds completely terrifying. It's a microscopic wrecking ball.
It would be terrifying, except that its immense power is also its greatest weakness.
How so?
Because it interacts so strongly and aggressively with everything it touches, it bleeds off its kinetic energy almost instantly. Its penetration power is practically 0.
Oh, I see.
Yeah, an alpha particle ejected into the air will smash into a few oxygen molecules and come to a complete dead stop within an inch or 2.
So if there is a chunk of an alpha-emitting material sitting on the table across the room from me, I'm completely safe.
You are entirely safe. The particles can't even reach you. Even if you walked up and picked the material up with your bare hand, the alpha particles would be completely stopped by the microscopic layer of dead skin cells on the surface of your epidermis.
They cannot penetrate to the living tissue.
Right.
But, and this is a massive fatal, but what happens if you bypass that layer of dead skin?
If you ingest or inhale an alpha emitter, the situation becomes catastrophic.
Like breathing in radioactive radon gas or swallowing a liquid containing polonium.
Yes, you are taking the alpha emitter and placing it directly inside your body, resting directly against your soft, living, vulnerable lung tissue or intestinal lining.
There is no dead skin armor on the inside of your lung.
Exactly. The alpha particles are now unloading all of their massive, bulldozer-like ionizing energy directly into your cellular DNA. It is a highly localized, devastating bombardment.
This is exactly the mechanism behind one of the most famous assassinations of the 21st century. The Russian dissident Alexander Litvinenko was poisoned in London.
Right, the assassin slipped a tiny amount of polonium-210 into his teapot.
And polonium-210 is a pure alpha emitter. Carrying it in a vial in their pocket was perfectly safe for the assassins. Sitting next to him while the tea steamed on the table was safe.
But the moment Litvinenko swallowed it, he bypassed his skin's armor. The alpha particles shredded his internal organs from the inside out, and there was absolutely nothing doctors could do to save him.
Just a grim reality of the physics involved.
Mm.
Okay, the second animal in the particle zoo is the beta particle.
Beta particles operate on a completely different scale. They are much, much smaller. A beta particle is simply an incredibly energetic, high-speed electron.
It occurs through a fascinating process. Inside an unstable nucleus, a neutron can spontaneously transform into a proton.
To conserve charge, this transformation generates an electron, which is instantly shot out of the nucleus at near the speed of light. That high-speed electron is the beta particle.
So it carries a -1 charge, and compared to an alpha particle, its mass is almost zero.
Because it is so light and carries half the charge of an alpha particle, its danger profile shifts. It doesn't bulldoze, it zips through matter, causing a trail of ionization, but a much less dense trail.
Its ionization power is lower, but its penetration power is significantly higher. It can travel further before hitting something and stopping.
Yes, a beta particle will blast right through a piece of paper, and it has enough kinetic energy to penetrate a few millimeters into human skin, potentially causing radiation burns.
But it can be easily stopped by a thin sheet of plastic, a piece of wood, or standard aluminum foil.
The third animal in the zoo is one we've already met, gamma rays.
Right, gamma rays often accompany alpha or beta decay. When the nucleus ejects a particle, it sometimes still has a bit of leftover excess internal energy.
It sheds this energy by firing off a pure electromagnetic photon.
So unlike alpha and beta, gamma rays aren't chunks of matter. They have zero mass and zero electric charge.
Which means they act like ghosts. They have the lowest direct ionization power because they don't possess a magnetic charge to forcefully rip electrons away.
They only ionize an atom if they score a direct physical bullseye on an electron.
And because an atom is mostly empty space, a gamma photon can zip through thousands of atoms without hitting anything.
But that means their penetration power is immense.
Oh, massive. A gamma ray will travel straight through your entire body, entirely unbothered by your skin or bones, perhaps hitting and ionizing only a couple of atoms along the way.
To stop a gamma ray, you need a substantial amount of incredibly dense material. Think thick slabs of solid lead or feet of high-density concrete.
And finally, we arrive at the strangest and arguably most complex particle in the zoo. The neutron.
Neutrons are uncharged particles ejected during specific types of violent nuclear reactions, primarily nuclear fission inside a power plant reactor or inside a nuclear weapon.
Because they have absolutely no electrical charge, they are entirely immune to the electromagnetic force of the electron clouds that surround atoms.
The electrons just don't repel them or attract them.
They just ghost right through the electron cloud as if it isn't even there. This means neutrons are indirectly ionizing. They don't strip electrons themselves.
Instead, they bypass the outer defenses of the atom and crash directly, physically, into the nucleus.
Exactly.
What happens when a rogue neutron slams into a nucleus?
It depends entirely on how fast the neutron is moving. If it is a high-speed neutron, it causes a violent event called spallation.
Spallation.
Yes. Picture a pool table. The nucleus is the tight triangle of billiard balls before the break. The high-speed neutron is the cue ball.
It smashes into the nucleus and physically blasts smaller particles, protons, or alpha chunks flying out of the nucleus at high speeds.
So the neutron breaks the atom apart, and the pieces that fly off cause massive secondary ionization.
But what if the neutron is moving slowly? These are called thermal neutrons, right?
Yes, thermal neutrons. When a slow neutron hits the nucleus, it doesn't break it apart, it gets absorbed. The nucleus swallows the neutron.
But now, the nucleus is too heavy. It has the wrong ratio of neutrons to protons. It becomes unstable.
The slow neutron literally turns a stable, safe atom into a radioactive one.
This is called neutron activation. The IAEA handbook notes that this is a major consideration in nuclear engineering.
For example, the stable sodium atoms in standard seawater or coolant water can absorb a stray thermal neutron from a reactor and transform into sodium-24,
which is a highly radioactive beta-emitting isotope. The physical structure of the environment itself becomes radioactive.
That is wild to think about. Neutrons can infect other matter with radioactivity, and because they ignore electron clouds entirely, shielding against them requires a completely counterintuitive strategy.
You can't use lead to stop neutrons.
You cannot. This introduces the concept of stopping power. Dense materials like lead are phenomenal for stopping gamma rays because a lead atom has a massive dense cloud of 82 electrons.
Gamma photons interact with electrons, so throwing a huge cloud of electrons in their path is highly effective.
But a neutron doesn't care about electrons. It flies right through the lead's electron cloud. And because the lead nucleus is so massively heavy compared to the neutron just bounces off it like a ping pong ball bouncing off a bowling ball.
It loses almost no speed or energy.
To stop a neutron, you need to hit it with something its own size. You need hydrogen.
Because a hydrogen nucleus is just a single proton, which has almost the exact same mass as a neutron.
When a flying neutron collides with a proton, it transfers a massive amount of its kinetic energy, just like two identical billiard balls colliding head-on. The neutron stops dead, and the proton absorbs the energy.
So to build a radiation shield against neutrons, you don't use lead, you use hydrogen-rich materials.
You use massive tanks of water, or you use special concrete that contains high amounts of trapped water molecules.
Okay, to summarize this particle zoo, I want to use an analogy I've heard physicists use before because it brilliantly crystallizes the danger profile of these particles.
Oh, a cookie analogy.
A cookie analogy. Imagine the universe hands you 3 radioactive cookies. One is an alpha cookie, one is a beta cookie, and one is a gamma cookie.
Okay.
You are forced to hold one in your bare hand, you must put one in your pants pocket, and you have to eat the third one. How do you survive?
Based on everything we just discussed about penetration and ionization power, the morbid choice is surprisingly clear.
You hold the alpha cookie in your hand. The heavy, bulldozing alpha particles will violently ionize the air, but they will be completely, 100% stopped by the microscopic layer of dead skin on your palm. You are safe.
You take a beta cookie and put it in your pocket. The fast-moving electrons have more penetration, but they will be reliably blocked by the fabric of your genes. You are safe.
Which means you eat the gamma cookie.
Wow.
The pure electromagnetic gamma photons have immense penetration, but incredibly low interaction rates.
The vast, overwhelming majority of those photons will beam straight out of your stomach, pass entirely through your tissue without hitting a single atom, and exit your body harmlessly.
It's an intense thought experiment, but it completely demystifies how we interact with these physical realities.
It really does.
Which is a perfect transition, because listening to us describe flying, atom-smashing particles and radioactive cookies makes it sound like we live in a sci-fi war zone.
But the truth is, you are swimming in an invisible ocean of these particles all day, every day.
We need to contextualize the actual numbers, which brings us to the data provided by the U.S. Nuclear Regulatory Commission on natural background radiation.
Before we get into the numbers, we have to tackle the units, because radiation measurement is notoriously confusing.
Oh, it's an absolute alphabet soup. You read one article and they talk about rads, another uses sieverts, another uses rems. Let's break it down so it actually makes sense.
The confusion exists because we are trying to measure two completely different things: physics and biology.
Okay.
The first unit we use is the gray, or in the older imperial system, the rad. This is a pure physics measurement of absorbed dose.
It simply calculates how much raw physical energy in joules was deposited into a kilogram of mass. It doesn't care if that mass is human tissue or a block of wood or a glass of water.
But as we just learned with our cookie analogy, the type of energy matters immensely. Depositing 1 joule of gamma ray energy into my lung is vastly different than depositing 1 joule of alpha particle energy into my lung.
Precisely. The alpha particle does 20 times more biological damage because it concentrates that energy into a dense path of total destruction, whereas the gamma ray spreads it out harmlessly.
So raw physical energy isn't enough for doctors. To measure actual biological harm, scientists take that absorbed dose, the gray, and multiply it by a weighting factor called the RBE, the relative biological effectiveness.
So for gamma rays, the RBE is 1, but for alpha particles, the RBE multiplier is 20.
When you multiply the physical dose by the biological effectiveness, you get the equivalent dose. And this is measured in sieverts, or in the US, rems.
1 sievert equals 100 rems.
This unit is the gold standard because it tells us the actual measurable biological impact on human cells, normalizing all the different types of particles so we can compare apples to apples.
Excellent. So using rems as our biological standard, the NRC reports that the average American receives an annual dose of roughly 0.3 rem or 300 millirems entirely from natural sources.
Just from the Earth existing.
Where does it all come from? We can break it down into terrestrial, cosmic, and internal sources.
Terrestrial radiation is simply the ground beneath our feet. The Earth's crust was formed with naturally occurring radioactive isotopes like uranium and thorium forged in ancient supernovas, and they have been slowly decaying for billions of years.
Which ties back to our introduction about the Capitol building. Granite contains trace amounts of uranium. Living in a brick or stone house slightly elevates your terrestrial dose compared to a wooden house. What about internal sources?
We actually carry radiation inside us. Because plants grow in the earth, they absorb those radioactive isotopes into their structures. When we eat the plants or eat the animals that ate the plants, we internalize it.
The classic example is the banana.
Yes, bananas and Brazil nuts in particular are rich in potassium. A very small, naturally occurring fraction of all potassium on Earth is the radioactive isotope potassium-40.
So when you eat a banana, you're ingesting a tiny amount of a beta and gamma emitter.
You are literally eating radiation, but obviously your body clears it out or uses it just like normal potassium. Then we have cosmic radiation.
Cosmic radiation comes from above. The sun is constantly blasting high-energy protons toward the Earth. And deep space, events like quasars and supernovas bombard us with immensely powerful cosmic rays.
Our planet's magnetic field and our thick atmosphere act as a massive shield, absorbing the vast majority of this cosmic bombardment.
But the shield isn't uniform. The higher up you go, the thinner the atmospheric shield gets.
Which means your geographic altitude directly affects your annual radiation dose. If you live in a high-altitude city like Denver, Colorado, you receive a significantly higher dose of cosmic radiation every single year than someone living at sea level in Miami.
Simply because there is less air above your head to intercept the particles.
And frequent flyers or airline crews get even more because cruising at 35,000 feet strips away a massive percentage of that atmospheric protection.
But the single largest contributor to our natural background dose, according to the NRC data, isn't the sun or our food. It's a gas.
Radon gas. It accounts for a full 2/3 of the natural background exposure for the average person. As the uranium naturally present in the Earth's crust slowly decays, it eventually forms radon, which is a radioactive noble gas.
Because it is a gas, it seeps up through the soil.
And because it is heavy, it tends to accumulate in the basements or lowest levels of homes with poor ventilation. You breathe it in, and as it decays inside your lungs, it emits alpha particles.
So we have zero point 0.3 rem from nature. To complete the picture, we add man-made sources. Medical diagnostics, your dental x-rays, mammograms, CT scans, add an average of about 0.04 rem a year.
Consumer products, like the tiny speck of radioactive americium used to make your smoke detector work, or luminous paint on analog watch dials, add a negligible 0.01 rem.
Add it all up, and the average total annual dose for an American is roughly 0.36 rem. Nature provides over 80% of it, and human technology adds the rest.
So when you look at a banana or a granite countertop, or the fact that you live in Denver, it is vital to understand that this 0.36 rem is not a hazard.
The human body and all biological life on Earth evolved over billions of years immersed in this exact radioactive bath.
Our cells possess incredibly robust, sophisticated DNA repair mechanisms that are constantly patrolling for and fixing the minor intermittent damage caused by this background hum of radiation.
The NRC explicitly states that absolutely no adverse health effects have ever been discerned from natural background levels.
That brings up the critical threshold, though. If 0.36 rem a year is the harmless background noise of the universe, what happens when you turn the volume up?
How does a physics event, a photon knocking an electron out of orbit, escalate into radiation sickness or cancer?
When we evaluate biological effects, we have to divide the timeline into two distinct categories: acute short-term effects from massive doses and long-term chronic effects from low-level exposure.
Let's address the acute effects first. This is the nightmare scenario. A nuclear accident or being too close to a detonation.
Acute radiation syndromes operate on what scientists call a threshold model. This simply means that the human body can absorb a certain amount of acute damage with zero outward symptoms.
If a sudden burst of radiation kills 100 cells in your arm, you won't even notice. Your immune system clears the dead cells and they are replaced.
But once the dose crosses a massive threshold, the physical damage overwhelms the body's ability to clear the debris and repair the tissue.
And the numbers provided by the NRC are sobering.
If an individual receives an acute whole-body dose of 350 to 500 rems, remember, your whole year is 0.36 rem, so this is over 1,000 times your annual dose delivered in a matter of minutes or hours. That dose will be fatal to 50% of the people exposed within 30 days, assuming no intensive medical intervention.
And what actually causes the death?
At those massive levels, the ionizing radiation is causing trillions of simultaneous chemical bonds to break. It halts cellular division dead in its tracks.
The most sensitive cells in your body are the ones that divide the fastest. Specifically, the precursor cells inside your bone marrow that generate white blood cells, and the rapidly dividing cells that form the delicate lining of your stomach and intestines.
So the radiation doesn't instantly burn you to ash, it destroys your body's ability to replenish itself.
Exactly. At a dose of 1,000 rems, over 99% of those precursor cells are instantly killed. Without white blood cells, your immune system collapses entirely.
Without the intestinal lining, your body cannot absorb nutrients and suffers massive internal bleeding. This is radiation sickness. It is a systemic failure of cellular renewal, leading invariably to death within weeks.
That is the horrifying reality of acute exposure. But what about the other category? What if you receive a dose that is well below the threshold for radiation sickness, but significantly higher than the natural background?
This is where we look at long-term effects, and the mechanism shifts entirely. Low exposures, let's say under 10 rems, do not cause massive cell death. You won't feel sick, and your organs will function perfectly.
But those flying particles are still randomly striking DNA molecules.
Going back to the thymine dimers we discussed with UV light.
Right. If a low-level dose of gamma or X-ray radiation strikes a DNA strand, it can cause a subtle mutation. Usually, the cell realizes it is damaged and undergoes programmed cell death, or the repair enzymes fix the code.
But occasionally, a mutated cell survives, evades the immune system, and lies dormant. 5, 10, or even 20 years later, that single mutated cell can begin to divide uncontrollably. It becomes a malignant cancer.
And this creates a massive headache for regulators. How do you legally regulate an invisible particle that might cause a tumor 2 decades from now?
To manage this uncertainty, the global radiation protection community, including the NRC, relies on a foundational concept called the LNT model. That stands for Linear No Threshold.
Let's unpack LNT, because it dictates the safety protocols for every hospital, nuclear plant, and laboratory on the planet.
The LNT model is a safety assumption. Unlike acute radiation sickness, which has a safe threshold before symptoms appear, the LNT model assumes there is absolutely zero safe threshold when it comes to long-term cancer risk.
It posits a straight, linear line. A massive dose gives you a massive cancer risk. A medium dose gives you a medium risk. And a microscopic, tiny dose gives you a microscopic, tiny risk.
So under the LNT model, every single ionizing photon that hits your body is treated like a lottery ticket. The more radiation you are exposed to, the more tickets you buy, and the higher your statistical chance of drawing the cancer ticket.
That is a perfect encapsulation. And because regulators must prioritize public health above all else, the NRC uses this ultra-conservative LNT assumption to set incredibly strict limits.
They mandate that public exposure from any man-made nuclear facility cannot exceed 0.1 rem per year. They are keeping the number of lottery tickets as close to zero as humanly possible.
But if we look at the epidemiological data, the actual medical history of human beings exposed to radiation, a really surprising narrative emerges about how dangerous those lottery tickets actually are.
This is perhaps the most misunderstood aspect of radiation. Ionizing radiation is terrifying, yes, but scientifically speaking, it is a remarkably weak carcinogen compared to other environmental factors.
The NRC report backs this up with some truly staggering long-term data. They have been meticulously tracking a cohort of 52,000 Japanese atomic bomb survivors since 1950.
These are individuals who survived the initial blasts but received massive acute whole-body doses of at least 0.5 rem, with many receiving exponentially more.
You would intuitively expect that population to be entirely decimated by cancer over the following decades. And unfortunately, there are about 8,000 cancer deaths within that group.
But scientists must compare that number to the statistical baseline of a normal population. Based on standard rates of cancer from smoking, age, diet, and general pollution, roughly 7,600 of those deaths would have occurred naturally anyway.
Which means out of 52,000 people who were subjected to the fallout of a nuclear weapon, only about 420 excess cancer deaths can be statistically blamed on the radiation.
420 out of 52,000. That drastically reframes the lethality of radiation.
And we see the exact same statistical trend when analyzing the worst nuclear disaster in history. The NRC data on the Chernobyl accident is illuminating.
Tragically, 30 emergency workers and plant operators died horrific deaths from acute radiation sickness within months of the explosion. They absorbed massive threshold-breaking doses.
But when epidemiologists track the general public, the hundreds of thousands of people in the surrounding regions who were exposed to elevated radioactive fallout, the data shows zero definitive, statistically significant excess cancer deaths linked directly to the radiation.
With the sole exception of a highly treatable form of childhood thyroid cancer caused by drinking contaminated milk.
That is genuinely hard to believe given the cultural mythology around Chernobyl. Zero definitive excess cancers in the general adult public.
It feels counterintuitive, but it highlights a massive canyon between public perception and epidemiological reality. Radiation is a hazard, and it absolutely must be respected, but it is not the apocalyptic, unstoppable cancer engine that movies portray it to be.
The human body is remarkably resilient. So if the actual risk of low-level exposure is incredibly small, but the regulatory bodies treat it with maximum caution, it sets the stage perfectly for how we interact with it today.
Because we so precisely understand the physics of the EM spectrum, the particle zoo, and the biological risks quantified by the LNT model, humanity has been able to flip the script.
We don't just hide from radiation, we harness it.
We use this dangerous, invisible force to build the modern world. Once you understand the mechanics of ionization and decay, it stops being a hazard and becomes an incredibly precise tool.
Let's talk about some of those applications. In the realm of history and science, we use the predictable nature of radioactive decay as a literal time machine.
Radiocarbon dating relies on carbon-14, a naturally occurring radioactive isotope created when cosmic rays strike the atmosphere. Plants absorb it, animals eat the plants, and when the organism dies, it stops absorbing new carbon-14.
And because physicists know exactly how long it takes for carbon-14 to decay back into stable nitrogen, they simply measure how much radiation is still emitting from a bone or a piece of wood, and they can calculate its exact age back tens of thousands of years.
It's a biological clock ticking away inside all organic matter.
And as we touched on earlier, our entire planetary infrastructure of communication is built entirely on the non-ionizing side of the EM spectrum. Every text message, GPS coordinate, and streaming video is just an encoded manipulation of radio waves and microwaves bouncing between satellites and towers.
But the most profound life-altering applications of radiation are undoubtedly in the medical field. Diagnostic imaging is entirely reliant on the physics of atomic density.
When you take an X-ray, the machine fires a controlled burst of high-energy photons through your body. The X-rays easily pass through the low-density carbon and water atoms of your soft tissue and hit the film behind you.
But they are blocked and absorbed by the dense calcium atoms in your bones. The resulting image is literally a shadow cast by your skeleton.
And then medical science took it a step further into the realm of pure science fiction with PET scans, positron emission tomography. When I read the physics behind how a PET scan works, my jaw hit the floor. We are literally using antimatter to look inside the human body.
It is arguably one of the most elegant applications of quantum physics in human history. To find a hidden tumor, doctors inject the patient with a special biological tracer. Often, it is a form of glucose sugar that has been tagged with a radioactive isotope like fluorine-18.
And tumors are incredibly metabolically active. They are hungry, growing tissue, so they greedily absorb that radioactive sugar faster than the healthy cells around them.
Now, the fluorine-18 undergoes a very specific type of radioactive decay. It undergoes beta plus decay, meaning it ejects a positron. A positron is the antimatter twin of an electron. It has the exact same mass, but a positive charge.
And what happens when matter meets antimatter?
Total annihilation. The moment that positron travels a millimeter through your tissue and collides with a normal electron, the two particles annihilate each other. They cease to exist as matter.
Following Einstein's E equals mc squared, 100% of their physical mass is instantly converted into pure electromagnetic energy.
And that energy bursts outward as two identical high-energy gamma rays traveling in exactly opposite directions, 180 degrees apart.
The patient is lying inside a massive ring of gamma ray detectors. When the detectors register two gamma hits on exactly opposite sides of the ring at the exact same nanosecond, the computer draws a straight line between them.
By calculating millions of these intersecting lines, the computer pinpoints the exact 3D location of the annihilation events. It builds a glowing real-time map of exactly where the hungry tumor is hiding.
We use antimatter annihilation to map cancer. That is breathtaking. And in a beautiful irony, we use the exact same ionizing radiation that can cause mutations to cure cancer by destroying the mutated cells.
Radiation therapy is the calculated, targeted application of the acute biological damage we discussed earlier. By focusing intense beams of ionizing radiation directly onto the tumor, oncologists purposefully trigger massive DNA damage inside the cancer cells.
The tumor's cellular machinery is shredded, it can no longer divide, and the cancer dies while the healthy tissue around it is carefully spared.
But operating these incredible machines requires stringent protection protocols. The safety guides from Barrio Technologies outline exactly how the professionals who work around this energy all day protect themselves without succumbing to the LNT model of cumulative damage.
The overriding philosophy in radiation safety is called the ALRA principle. It stands for as low as reasonably achievable.
It dictates that even if the risk of a low dose is microscopically small, you must still take every practical step to avoid it. ALRA is built on three foundational pillars: time, distance, and shielding.
Time and distance are straightforward math. Limit the amount of time you're exposed to the source and maximize your physical distance from it. Because radiation spreads outward in a sphere, stepping just a few feet backward exponentially drops the number of photons hitting your body.
But when you can increase the distance, you rely on shielding, putting massive, dense atoms between you and the source. Which brings us full circle to the lead apron the dentist drapes over your chest before taking an X-ray.
Based on the physics of the particle zoo, we know exactly why they use lead. Lead is a high Z material. It has a massive atomic number. A single atom of lead contains a heavy nucleus surrounded by a dense, sprawling cloud of 82 electrons.
And because X-rays and gamma rays are electromagnetic photons, they primarily interact with the electron clouds of the atoms they pass through.
Forcing those high-energy photons to navigate through a dense forest of lead atoms, where each atom presents a massive 82-electron target, guarantees that the photons will crash, transfer their energy, and be completely absorbed before they ever reach your vital organs.
The lead apron acts like a dense catcher's mitt for quantum bullets.
Which leads to a thought I think a lot of listeners might have right now. Let's say you are scheduled to go into the hospital tomorrow for a diagnostic CT scan.
Yeah.
We just established the LNT model, the regulatory assumption that every single photon of ionizing radiation adds a tiny fractional risk of cancer. How should that patient mentally balance the incredible diagnostic benefit of the scan against the statistical risk of adding those photons to their lifetime dose?
The operative word in the LRI principle is reasonably achievable. The medical and scientific communities do not demand zero exposure, because demanding zero exposure would mean abandoning the life-saving benefits of X-rays and PE scans.
The decision is always a calculated risk-benefit analysis. The immediate, tangible benefit of a CT scan detecting an internal hemorrhage, spotting a tumor early enough to operate, confirming a complex bone fracture, vastly, overwhelmingly outweighs the microscopic, theoretical, statistical risk added by that single diagnostic dose.
Especially when you remember that your body is already expertly handling a constant hum of background radiation every single day.
Exactly. When you understand that radiation is not an unnatural poison, but a fundamental energy transfer that your biology has evolved to tolerate and repair, you can comfortably accept the medical use of radiation as a powerful, precisely calculated tool rather than an unknowable hazard.
That is an incredibly reassuring framework.
Let's recap the journey we've taken today, because we covered an immense amount of ground. We started by deciphering the cosmic piano of the electromagnetic spectrum, learning how the miles-long radio waves discovered by Hertz, the visible light of the sun, and the microscopic X-rays discovered by Röntgen are all just different frequencies of the exact same phenomenon.
We established the Great Divide, that critical 10 electron-volt threshold separating the safe, non-ionizing vibrations that heat our food from the dangerous bond-breaking power of ionizing radiation that can mutate our DNA.
We met the aggressive heavy alpha particles, the fast-moving beta particles, and the ghostly nucleus-smashing neutrons in the particle zoo.
We looked at the numbers and realized we are living in a naturally radioactive world, swimming in an ocean of cosmic rays and eating radioactive potassium in our bananas.
We demystify the LNT model to understand how radiation actually impacts public health, proving that while it must be respected, it is not the boogeyman pop culture claims it is.
And finally, we saw how humanity has tamed these fundamental forces to date our ancient history, build our global communications network, and heal our bodies with antimatter.
It truly is a remarkable testament to human curiosity and scientific progress. We took an invisible, potentially deadly force of nature, decoded its exact mathematical rules, and turned it into the bedrock of modern civilization and medicine.
It really is.
But I want to leave you, the listener, with a final provocative thought to mull over. Everything we've discussed today, the 0.36 rem background dose, the ozone layer miraculously protecting us from UVC rays, the Earth's magnetic field acting as a deflector shield against cosmic bombardment, all of this is incredibly specific to planet Earth.
Right. Our entire biological evolution has taken place inside this highly curated, perfectly shielded terrarium.
But as humanity looks to the stars, the rules change. If we eventually leave Earth to live in deep space, or if we establish permanent colonies on Mars, a planet that entirely lacks a thick atmosphere and a global magnetic field, we will be leaving those shields behind.
The settlers on Mars will be exposed to a radically higher, unrelenting baseline of cosmic rays and solar radiation.
Which means humanity will be forced to adapt. Will our future biological evolution literally be dictated by the exact same radiation we spend so much effort hiding from today?
Will the humans living on Mars thousands of years from now eventually evolve incredibly robust, supercharged DNA repair mechanisms just to survive the ambient radioactive hum of their new home?
Will they become fundamentally biologically different from the humans left on Earth?
It is entirely possible. In biology, the environment always shapes the organism, and in the environment of deep space or the surface of Mars, ionizing radiation is the absolute dominant environmental factor.
It brings us right back to the very beginning. We like to think of biology and medicine as a clear, binary X-ray. It's either broken or not broken. It's either perfectly safe or completely dangerous.
But the reality is that we are swimming in a complex, murky, energetic ocean of fundamental forces.
The radiation passing through you right now isn't just a hazard. It is a window into the invisible, vibrating universe that made us, that sustains our modern lives, and that might eventually force us to evolve into something entirely new.